before we go to the third law, we need to just check out the units. So using F equals ma, the mass is in kilograms in the SI system. The acceleration is meters per second square. So this becomes the dimensions or the units for force, kilograms, meters per second square. And this combination of units in this way is written as a Newton, or the symbol is N. So the unit of force becomes a Newton written with a capital N, but written with a lowercase Newton in this way, not with a capital letter. That will become the person Newton, and this is the unit of force, Newton. So that becomes a unit of force, and this means that if you take 1 kilogram, and if it's accelerating at the rate of 1 meter per second square, then the force that's doing that is 1 Newton. Or a force of 1 Newton will accelerate 1 kilogram at the rate of 1 meter per second square. The US customary system is a pound, and 1 pound is equal to 1, again, mass times acceleration. So mass is a slug, if you recall, and the acceleration is feet per second square. So 1 pound is that force that accelerates 1 slug at the rate of 1 foot per second square. Newton is somewhat smaller. 1 Newton is almost a quarter of a pound. So a pound is like 4 newtons. Now let's do a small example also over here before going to the third law. This is page 4. So let's just say we're looking from above and we have an object of mass 5 kilograms, and that's the x-axis, that's the y-axis, and you tie a string to it and you pull, let's say tie it in the center, and you pull in this direction with the force F1 that is 20 newtons at minus 30 degrees. This angle is negative 30 degrees because it's below the positive x-axis. And there's another force that's at a bigger angle, let's say around 50 degrees, and the force is also bigger. So F2 is 40 newtons, so length should have been double at 50 degrees. So which way is this object going to accelerate, and what will be the value of the acceleration? So we'll use our equation. The sum of forces equals ma, and the forces are F1 and F2. F1 and F2 at 50 degrees. So it's going to be, we first need to write F1, and it's always better to write it in vector notation. So this is going to be the magnitude of F at times the unit vector of F, which is going to be cosine of minus 30 I and sine of minus 30 j. And that's the magnitude. So that will be the F times this unit vector. And the F is 20. Cosine of minus 30 is what, 0.866 I. And this is negative of sine 30 is minus 0.5 j. That becomes 17.32 I minus 10 j. So that is F1. And similarly, F2 can be written as 40 cosine 50i plus 40 sine 50j, which is 25.5 28.71i plus 30.64j. And then the resultant vector, resultant force, is F1 plus F2, and we add the I with the I, so it's 17.32 plus 25.71i, and we add the J with the J, so it's minus 10 plus 30.64 J. Never ever add an I with a J. Okay, I's can only add with I's, and J's can only add with J's, and that becomes 43.03i plus 20.64j. So now we can write that as R equals MA. This is F1 plus F2, and so the acceleration is going to be R over M. So the acceleration vector will be 40.03 over 5i, because M is 5, plus 20.64 over 5j, and that comes out to 8.61i plus 4.13 j meters per second square. That is the acceleration. Now if you want to find the magnitude of the acceleration, just square and add and square root. It's going to be 8.61 square plus 4.13 square root, and you can solve that. And the theta would be tangent inverse of the y term over the I term, and you can get that also. Now it would appear to be somewhat, because this vector is bigger, it should go somewhat in this direction, but that can be figured out. Okay, so we stop here.